Good evening, everyone. I hope that you survived the first unit of stats well. Now it's time to begin our second unit, numerical methods for describing data. Okay, so in this unit, we're going to look at what we sometimes refer to as one variable statistics, or when we have a single data set, like what can we conclude and what can we calculate based on the results of collecting one set of data from a sample. So in this unit, um, the good news is we're going to finally really do some real math. I mean, not that the stuff we hadn't done before wasn't real math, but here we're actually going to do more calculations using the calculator. Um, I will pull out my electronic Inspire, uh, which I'll do in future lessons to work on that. That'll be kind of interesting. Um, so I have to get that set up yet. We are going to describe the variability of data. We're going to look at box plots and this lovely thing called a z-score. Z-score is actually a very useful tool that you can use to compare a data point to the rest of the data without, any uh, revealing of what some of that data is. Like for example, um, you can use the concept of z-score to figure out how well you did on your test relative to the rest of the class without actually knowing how other people did on the test specifically. Um, that's to avoid things like privacy concerns, whatnot. Um, I'm not the kind of teacher that likes to tell the class, hey, so and so got a 96 on the test, good job, or so and so did not do well on the test. Like, clearly, I'm not going to say stuff like that. So, to avoid those sorts of concerns, we can use something called a z score that can give you information on to how well you did. And it's also used to characterize points based on where they are along a curve. Okay, so these are some of the things that we're going to look at. So let's get started. Our very first lesson has to do with just the mean and median itself. So, lesson one, the chewy, nougat filled center of a data set. Well, after all, it is just after Valentine's Day, and kind of have candy on the mind, right? Okay, so anyway, let's get down to some statistics that we're going to need to know going forward. On this page, what you actually see is a listing of some of the different variables that we use for different things. So you'll know, number one, that I hardly ever use the word average. The word mean is really kind of the official word that we use for the the result of a data set when you add them up and divide by how many you have. Um, so you might have used the word mean or average before, kind of interchangeably. Here we're going to really use the word mean. Average. Um, when we think of a point that's average, we think of a point that's sitting near the mean. Okay, so here are some basics that we're going to use throughout the rest of the course. So x will always be the variable for which we have sample data. So whenever I collect a set of data from a sample, whether I'm collecting, you know, weights of backpacks or shoe sizes or whatever else, that as a collective group is called x. Not so much a single number, but x just by itself represents the data set. Now, n will always represent sample size, so the number of observations that we've taken. That is consistent throughout the entire course, and there are no exceptions to that. So if you see the letter N written somewhere in the work that we do, it will always refer to sample size. To the point that we never even define it after this. Now that we know what N is, I'm just going to use it. And X, same thing. X and N will always refer to the amount of sample data, the number of observations. So we always use those. Y, once we get to it, we'll use the letter Y to represent response data for like a second sample set. So we'll get to that a little bit later on. So you'll always see subscripts to refer to first observation, second observation. So x sub 1 is usually the first thing in the data set. X sub 2 is the second thing, all the way down to x sub n. And x sub n is the last observation. Now, you could even potentially see something like this. I might write x to the n minus 1. And if I write this, this is the second to last data point. So, you could see something like that. Oops. Don't need that. Okay, so, and then the next to last data point beyond that would be x sub n minus 2, and usually we don't have to go that far. We really only, though, will see x to the n minus 1 if we're doing like true AP work. We probably won't see it much in this course, but it's there just for completeness sake. Okay, so what is the mean of a data set? The mean of a data set is adding up all the observations and dividing by the number, right? You've probably been doing that for years upon years, right? However, we're going to formalize it with some symbols, okay? Because adding all of them up and dividing by how many you have isn't a formula, it's a description. Now, that does tell us how to calculate it, but how can we write it as a nice closed formula? So the first thing that we're going to look at is some symbols, right? So first off, x with the line over it. The x with the line over it always refers to sample mean, okay? So the bar over x is the official for sample mean. And whatever letter I use here, if I'm using x or y, or I might even have different data sets of x, whatever it is that we're looking at, the bar over it will always mean the average of them. So the big kind of crooked E, if you've never seen this before, that's the Greek letter sigma. And it represents the sum of. So that letter is used as a shortcut to say we're going to add a bunch of numbers together. But what numbers are we going to add? We're going to add all of x. So this is saying the sum of all x values divided by the number of data values. And n, as we said, always represents sample size. So this formula is exactly the description of average. We are going to add them all up, so all the data observations, and then divide by how many we have. So in this particular case, there's no wiggle room. There's no different ways to kind of interpret this. So x with the line over it, as I said before, represents sample mean. And most of the time, that's what we use is sample mean. We collect a sample from the population, and then we use that to try to determine what's going on in the entire population. So what about the entire population? The entire population is represented by Greek letters. Okay, here we go with the Greek letters again, right? So you might remember this if you've taken physics. You know this symbol, I believe, is a coefficient of friction, if I want to say. Correct me if I'm wrong on that one. So mu is the Greek letter m, and so we use it in stats because, well, m begins with m, or mean begins with m, so it makes sense to use the Greek letter for that. Now, kind of interesting reason really why we use Greek. Yes, it's homage to the Greeks who did a lot of work in math, many, many years ago. But also, to most of us who don't speak Greek, these letters are pretty much unknown to us. So we use them to represent truly unknown quantities. So the population mean is the mean of all the values in the population. We don't know what this number is most of the time because if we knew this, why bother doing stats? If I knew that the average weight of the backpacks of every student in the building is 9.38 pounds, then why would I need to do a survey about it? Or what if I knew that exactly 471 students ate lunch on a daily basis? I wouldn't need to do any statistics on that because then I would just know. So we give it a letter to represent the population mean, but we almost never know its exact value. Our goal is to estimate. So here's the thing. So really what it boils down to is the mean, sample mean, is an estimate of mu. So what we're doing is this we can find. We take a small sample of data and we calculate this. And so our question is, how close is this to mu? Now, obviously, that's a question we can't answer exactly because if we did, we would know mu. And then why do? So instead, what we are going to do is we are going to use some tools that once we find this, the sample mean, we're going to then say, based on what we know about our sample and what we've done, what we've collected, potentially how close could mu be? And so what that's going to do is tell us approximately in what range might we expect to see the population. That's kind of how we're going to do this. As you can imagine, the more sample that you collect, the closer the sample mean gets to the population mean. So eventually, I'll mark here, and I'll draw a little arrow to kind of illustrate this. So I'm going to illustrate this, and that's because we'll say bigger sample, closer to the true population. And that's a big tenet of statistics. Now, larger samples aren't always better, but generally speaking, you will be closer to the population mean with a larger sample. The sample mean, as I said, is considered an estimator. Our job is then to think about, is it a legitimate estimator? Like with the data I've collected, is there bias? Is there some reason why my sample won't reach the population, or maybe it will? So we'll come up with all of that as we go along. Okay, so in class, we're going to do this interesting activity involving class shoe size. We'll skip that for now because we can do some other things with this. We can illustrate mean and median a different way. Okay, so the median of a data set is another middle. Put the data in order, determine the middle point, right? We've done that. Even in this class, we've done that a few times already. However, do keep in mind that because of this, there is no formula for median. Because putting the data in order and determining the middle point, there's no mathematical function that orders a set of data. There are algorithms that can sort data and put them in order. Shell sort, bubble sort, things like that. But that's like more computer sciencey kind of things. So there's that. But this is not an algebraic formula. It's still a process, and we can still determine the middle point. Keep in mind, as we've already discussed, if there's an even number of observations, then the median is in between the two observations closest to the middle. So it's the mean of the middle two numbers. Okay, so Now, it says from our previous work here, that is from the activity that we didn't do because we're going to do that one in class. But you'll see how that plays out on some of the next work. Okay, so now that we kind of understand a little bit more about mean and median, um, so those are things you probably already knew, outside of maybe the uh, sigma and the formulas, okay? Um, but what are we going to use in this class that's different? Okay, so what we're going to look at is the idea of shape, center, and spread. Remember we did this before: shape, center, and spread. Well, mean and median, right? Oops. Mean and median are measures of center. And remember in the beginning we did this, we simply just looked at median because it's easy to see with a small set of data. But now that we can take off the calculators, we can put data in, we can find the average, right? Now, the average or mean and the median, both of those numbers are measures of center. However, they often give different answers. But how can they be different and both measure center? Well, they look at the problem in different ways. So, median is like the physical center of the data. The mean is more of like a balance point. Like if you were to put the data on a number line and attempt to balance it, it would balance right around where the mean is. So, what becomes important then is how much they agree. Because if they do agree, that tells us a lot about the data. And if they don't agree, that can tell us a lot about the data too. So that goes into now the connection with shape. So most data in statistics that we use follows this bell curve. So what the bell curve represents is the idea that data tends to be mostly concentrated around where you'd find the mean and median. So that when you collect data from a population, or by way of taking a sample, most of the data is going to be within a little bit of what the mean and median would be. So most of your data is going to be clumped near some center point. However, you will have likelihood some data points that are a little different. You might know those as outliers. Well, outliers are not common pieces of data, right? And outliers are farther away from the mean and median. So it turns out that for most data, the farther you go from the mean and median, the less likely you are to see data out there. Therefore, what happens is good data tends to form this mound shape that we call the bell curve. So that bell curve can not always be perfect, but sometimes it can be skewed to one side. Uh, but the lovely part is that if the mean and median of a data set are approximately equal, so within about 5% of one another, so if one of them is 5% or less larger than the other one, whichever direction it goes, um, then you have a very clear balanced center, and then the data will kind of coalesce around that. And so you have this shape that takes like this nice symmetrical mound. So one way that we can tell shape, you know, in unit 1 when we did this, we looked at shape and we made our best intuitive visualization. So sometimes data was symmetrical, kind of. And I think on the test there was one that's it's kind of symmetrical, it's kind of skewed, it's got a maybe an outlier, and it's you don't really make a very strong argument to it, and so you can defend a lot of different answers. However, now we're adding a tool to help you make the difference, and that tool is this: if the mean and the median are pretty close to one another, that is an indication that the data is approximately symmetrical, even if the data might have an outlier here or there. So that's why I say approximately equal, and the data will be approximately symmetrical. So that's very important. It turns out this is pretty consistent. Now, what happens in some other cases? So we've talked a little bit about skew. When data is skewed, the mean increases and the median stays mostly consistent. And the reason why this happens is because data with outliers on the upper end, right? So, say you've got a data set and you have some really unusually high points. So, those unusually high points will affect the calculation of mean because that is a calculation. So, a high point will affect that and pull the mean towards higher numbers. However, the presence of an outlier does not affect where the center, physical center of the data is. You'll see that really kind of happen in a little bit. The same thing happens on the other end, where if you have a low end outlier, then the mean ends up being lower than the median. And the more unbalanced those points are, the more skewed the data set ends up, and then the farther apart the mean and median get. So if you think about it in terms of percentage increase and decrease, like we did in Unit 1, the farther away they are from one another, the more skewed you can say the data set is. So, like, if the mean is, say, 50% higher than the median, then that's telling you that it's probably pretty well skewed. Something like that, right? So, it's an extra tool to tell us. But let's see the numbers of this in person, like really in action, to see how this happens. Okay. Yes, the mean is very receptive and influenced by outliers. The median is often very resistant to them. You can change the median by adding lots of data points. However, if you start adding lots of outliers, they really no longer become outliers. More on that later. Okay, here's the situation that kind of illustrates this. So back in 2013, so my advisory group, not my current one, but this is a few groups ago, I was collecting data on how how much community service that they did. It's kind of an interesting scenario. So back then, I think the requirement was, I want to say back then the requirement was 20 hours. Maybe it was 15, I forget. Actually, I mean, based on this, I guess it would say it was 15 because everybody did complete what they had to. So I had 10 students in my advisory, and so one person did the bare minimum of 15. Then I had a few other students. One did 20, a couple did 30, and this is the paperwork that I got. Some did 35, 40, 52, 75, 1,670. Yes, that is a legitimate number. The amount of community service performed by the students in my 2013 advisory, these are the legitimate numbers that you are seeing here. So let's describe this data set. What do you notice? I mean, sure, most of the points seem pretty well within a nice little range here, pretty symmetrical until you get to that last point. That is definitely an extreme outlier. Now, if you're wondering where that comes from, so what I told my students every year is that the minimum is 15 hours, but if you turn in papers to me, I will count them and I will add them all up. And so this one student said to me, "Hey, I have this stack of papers. Like they keep giving me these papers, like for a church youth group, and I just happen to have them all. You can look at them if you want." And I said, "Sure." And to my surprise, he handed me a stack of paper that had to have been about 3/4 of an inch of just solid papers. And I was a man of my word. I went through every single paper and added up all the hours. 1,670 was the final total. Um, so let's calculate the mean and median here, right? So let's start with the median. Median's easy enough, right? 1, 2, 3, 4, 5. Okay, let's split the data set in half, right? 10 numbers. So here's an easy case. The median is halfway in between the two middle numbers. Well, clearly, that's 35. So the median is 35. Now, as far as average, well, that's easy. We just have to add them all up, divide by 10, right? So let's go ahead and do that. Let's pull my calculator over. 15 plus 20, so we got 35 plus 60 plus 70 plus 40 plus 52 plus 75 plus 1670. That's 2002. So that's a total of 2002 hours. So the average, we divide by 10. And so the average is equal to 200.2 hours. And the median, 35. Okay, quite a bit different, right? That's a difference of nearly 6 times. Wowzers. Okay, so the average is almost 6 times higher than the median. So that does tell us that it's very, very skewed, right? Now, if I had to report a single summary measure to the principal about the class's performance. So I actually did this. I told the principal that year, it was a different principal, and I told him that the students in my class did an average of over 200 hours of community service each. Ooh, he was impressed. Now, was I wrong to say that? Technically, no. That statement is true. My students did an average of 200 hours of community service each. But is that number accurate to the population? Now, not only is that number not accurate for the 9 students who did like what you'd normally expect for community service, that number also is not indicative of the one outlier student either. So the 200 hours in this case is actually not a number that's useful to us. So this summarizes no one. So the fact that the median of 35, that one, yeah, that one's um, a little bit more true to what the population is doing. Yes, we know that one person did a lot more than that. However, that person can take some solace in knowing that they are definitely well above the median. Um, and clearly, there's not many students in the school that would have done more than that community service. Or have they? Here's another thing to think about. Um, is that student really an outlier? So remember, I said that that particular student came up, he got that number from church youth groups. I venture to think there's quite a few students in our building that attend those sorts of camps. They do counselor work during the summer. They do those sorts of activities and garner volunteer hours. However, because their school only has really a requirement for 15, 20 hours, most people will only bother to submit the paperwork for what they have available. Only submit the paperwork that they need, right? This particular person, he said he just happened to have it all printed out. And then I had to take it and count it all. If I said, no, that's okay, just give me what you, just, give me something, he probably would have just, written down, that he filled in his basic, 15 hours, maybe a little more than that, and that would have been it. So I venture to think that that number is a number that's not really truly an outlier. I bet there's a lot more students that have community service at or even above that mark, even in that group, um, or even, you know, in the building at that particular time that I did this, 2013. Um, that brings us to an idea of measurement and how we collected that data. And is that fair to have such a wacky outlier? So I kind of jumped around a little bit on that one, but essentially, the moral of that is, the mean and median are really different. The data set is really skewed as a result. Um, but does that number truly reflect what's happening? And if it's such a huge outlier, can we verify that data? And if not, why not? Okay, so I mentioned down here that there may be a way to compromise on this because the median, here's the problem, the median, there is, doesn't really take into account outliers. However, if I do try to take into account the outliers, it's a problem because that skews the data. So one thing that can happen, I'm only going to briefly talk about this because this won't be on quizzes or tests or anything. It's something called a trimmed mean. Um, in a trimmed mean, the left and rightmost values are chopped off. It's given as a percentage of how much of data is trimmed off of each end. So one thing that you could do um, is in a data set like this, you can take off the lowest and highest point and find the average of the rest of them. And in this case, what you would have is you would have a 10% trim. And you would be taking the average of the middle 80% of the data. And what happened is you get an average of about 40 if you did that in this particular case. And that number bumps up a little bit from the median and takes into account most of the spread, maybe not all of it. So, one thing that can happen as we deal with this trimmed mean, so crossing off like the lowest and highest and refiguring out the means, what you could do is use that to figure out like how symmetrical really is the data. Because in a case like this, here's some data from one year when I collected data on shoe size. I trimmed off one data point from both ends, and I get a mean of 9.93. I trim off two data points from both ends, and I get a mean of 9.92. And that's kind of telling us that the data is pretty symmetrical. That no matter how I collect this data, how I find the average, or what group I find the average, it looks like it's right around 10. So this is one way that we could potentially use to help see some more trends. But we're not going to worry too much about it more beyond this. Really, it's kind of knowing the difference between mean and median. Okay. All right, there's one last thing that we can talk about here in this lesson, and that is what to do with proportional data. So from now on, we're going to have two different kinds of data. We're going to have numerical data, and we did this kind of, remember, way back, like the very first lesson. We looked at categorical or what we call qualitative data, versus number data, or what we called quantitative data. And it turns out the analysis of those has to be different because one, you're dealing with numbers, and one, you're dealing with words. So, in order to turn category data into numbers, right, we can't find the average the same way that we can just take all the numbers and add them up and divide by how many we have. That doesn't work for categories because I can't add blue eye plus blue eye plus blue eye plus green eye plus green eye and average them and get teal. That doesn't make sense. Um, that'd be kind of interesting, though. uh, so we can't do that. Instead, what we do is we use proportional data. So most categorical data comes in groups where we can figure out what proportion of the group is each particular category. So, however, generally what we do is we focus on one category at a time. So let's talk about eye color, right? So if we deal with eye color, let's say I've got a sample and I deal, let's say I ask a bunch of people, I got blue eye, brown eye, green eye, brown eye, blue eye, green eye. Okay. So let's say I've got that data. And we'll use R to represent brown, okay? So I could, separate them in terms of categories, right? So I've got 1, 2, 3. So it looks like 3/8 of the data is blue eyes, right? And so, 37.5% blue. It looks like I'm going to have 37.5% brown and 25% green. However, it becomes really hard in statistics to deal with data that is built into more than two things, because the math behind it then, could differ. It's hard to describe it, but for those of you that took discrete math, I want you to think about some of the wackiness that can happen when you have three people in an election. When you have two people in an election, right? And we remember when we did all that voting stuff, and like you had a clear winner. It's either tied 50-50 or somebody won. Here, you kind of have the same thing, and then it becomes very difficult to look at one particular value when the others may be the same, may be differ. It's kind of hard to describe now, but essentially what happens is it becomes too difficult to look at the connections between three different things. So instead, what we do is, instead of separating into blue, brown, and green, instead we're going to have, let's say, blue and not blue. 62.5% not blue. And so either you do or you do not. And so we consider that a success and a failure. And then that way, we only have two things to compare, either the thing that we want to know more about, the thing that's considered our variable of interest, or everything that is not. So we're going to look at proportional data this way, even though we may have a list of data that we've collected with multiple different outcomes. So when we do that, then we have a variable called p hat. Yes, it's got a little hat on it. P hat. And it's the number of successes divided by n. So it's the proportion of how many times your observation happened in the data set. So in the last problem we did, 37.5% of people responded that they have blue eyes. So I would say that p hat equals 0.375. And so this is a number that we're going to use when we talk about categories. Okay, so that has a whole different system of math that we're going to use. And as we go through stats, we're going to learn at this kind of parallel. What do we do with number data? What do we do with category data? Okay, So the last thing that you could do, um, it's kind of an interesting activity. If you've made it all the way to the end of this video, one final task that I can have you do is this little thing here. And pick 5 numbers, find the average, subtract that average from each data point, and then add those results together. And I want you to see what you come up with. So pick 5 numbers, any 5 numbers. Um, and I'm not going to actually do this one here. I want you to do it if you've reached this far in the video and see what you come up with. Um, I wonder. This is actually going to help get us ready for lesson 2. Because the next thing that we have to do after this is how to deal with the spread of a data set. So in this lesson 1, we looked at the shape and how it connects to center. Our next lesson, lesson 2, we're going to look at spread of the data, which is actually a lot more than just range or typical values. More on that in our next video. Okay, guys, so here we learned a lot about mean and median. I'm going to leave it here, guys. It's about, hey, look, I'm about the 42-minute mark here, which is about the length of a normal class time. So, hey, perfect. Look at that. All right, folks, have yourself a lovely evening, and I will see you in class.